All right, welcome to the final lecture for Chapter 2, Atoms, Molecules, and Ions. Today's lesson will cover sections 5, 6, and 8. We'll be skipping section 7, which is on organic compounds. You'll have a whole semester of organic chemistry should you go that far, and nothing in this is going to be critical to anything else in the rest of this semester. Section 5 is periodic table of the elements. So we'll be talking about the periodic table here, and the periodic table is a table that lists or shows all known elements. These elements are going to be ordered by increasing atomic number. Starting with hydrogen being the first element of the periodic table and ending with oganesson. As far as we know, currently it has 118 protons. All right. You could say it is split up into many groups or families. And those are the columns of the periodic table. And then as well as periods, which will be the rows of the periodic table. Periodic law states that chemical and physical properties are going to be repeated throughout the periodic table, hence why we call it periodic. So in a sense, the elements have been placed where they are in the periodic table because it turns out, 2 elements or 3 or 4 or 5 may have the same or similar chemical properties and physical properties, and trends in certain properties change throughout the periodic table in a repeated fashion. And so you can see the current periodic table of the elements here. All the elements are there. All of them are named. There's 118 of them. And you can see like when they were discovered. You have before 1800, then you have from 1800 to 1849, 1850 to 1899, 1900 to 1949, and then I would say 1950 until current. The last set of elements that we discovered and named was really only completed about 3 years ago. So things like oganesson and flerovium and nihonium, those probably were maybe they were discovered around then, but verifying that they were actually atoms of those elements and proving that might have taken some bit of time. So as I mentioned, we have groups and families in the periodic table, and those will be each of the columns. In groups and families, or atoms in groups and families, they exhibit the same or similar chemical properties. That is a key thing. So, for example, if you go back to the periodic table, you'll see in the far left column of it, or the first group, those are known as the alkali metals. Here I'll put group 1 for now. All right, those elements in group 1, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, all chemically do essentially the same things. So the biggest difference will be in the rates of reactions, how fast these things move around, how big they are. The atoms can affect certain things, but for the most part, they're going to behave in essentially the same way. the alkaline earth metals will be in what we call group 2. And again, those are going to have similar or same chemical properties. That would be the second from the left column, which consists of beryllium, magnesium, calcium, strontium, barium, and radium. The halogens are in group 17, and so those, again, have similar chemical properties. You have fluorine, chlorine, bromine, iodine, astatine, and tennessine, which is another one of those newly discovered elements. We don't really know much about tennessine or oganesson or any of those really new ones because they've only made, a handful of atoms literally, and so it's tough to study their chemical properties. But we would make the assumption that it would behave similarly to those other halogens based on where it is. How that it would be the case is something that we'll discuss later on in this semester, in our next unit, in fact. So predicting its properties is not something that's irrational to do. And again, we'll see that later. The noble gases are in group 18. These are also known as the inert gases. Inert meaning they don't react, they're not reactive. Another reason they're called noble, they're too good for reacting. Those consist of helium, neon, argon, krypton, xenon, radon, and again, oganesson, which, again, we wouldn't really know for sure, but we can make assumptions. And then you have the transition metals. The transition metals will be in between groups 3 and 12. So there's 10 of those groups in the middle of the periodic table. Groups 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and below. Now, technically, I'm going to add a little caveat here. That caveat would be that the transition metals are only in, let me change the color back to black. They're only in periods 4 through 7. All right. And then the inner transition metals, these elements are in the bottom 2 rows. And they consist of 14 groups. And they're not going to be numbered. They're set below the periodic table, and the reasons for that I'll discuss in a minute, but they are almost always shown below, and so we call them the inner transition metals. Periods are the individual rows of the periodic table. Each period will consist of the same set of properties in the same columns or groups in each row. I'm going to put here throughout the groups. So Dimitri Mendeleev is the person who is credited as having created the periodic table in 1869. He recognized that certain elements would have the same properties as discussed earlier. So like fluorine, chlorine, and bromine, he noticed, had similar properties in their masses. He actually ordered them by mass, not atomic number. But he noticed that the elements next to those on the periodic table, like oxygen, sulfur, and selenium, also behave similarly to each other. And then you go down by mass 1 from each of those to nitrogen, phosphorus, and arsenic, and those had similar properties to each other. And so he realized these properties are repeating, they're periodic. Let's just put them into this table where the properties go from left to right, and then the rows are the repetition of those properties. increasing by mass. Later, it came along to change it by atomic number because certain elements, like tellurium is element 52, it has a mass that's greater than element 53, which is iodine. But actually, Dimitri Mendeleev noticed that that was the case, but he put tellurium below selenium in the periodic table because he knew that its properties chemically were similar to selenium and sulfur and oxygen, not bromine, chlorine, and fluorine. And he noticed that iodine behaved more like bromine, chlorine, and fluorine, not oxygen, sulfur, and selenium. So even he recognized that there were errors by doing it by mass, and he just fixed it. And further information came along later. Again, this was 1869 when he made the periodic table. Protons weren't officially discovered for almost another 40 years, slightly more than 40 years. So that's when it was realized, hey, we need to order them by atomic number, by the number of protons, not by mass. We could further classify elements as being either metals, nonmetals, or semimetals / metalloids. And in some ways, the character of being metallic or non-metallic is a trend that we see going in each period of the periodic table. So I'm going to put over here on the side in not green, but metallic character. And we'll talk about what that means in a minute. Increases to the left and down in the periodic table. So meaning if you go from right to left in a row, the elements become more metallic. If you go from top to bottom in a group, they become more metallic. And we're going to talk about other trends like this in the periodic table. So I'm going to represent that as a downward to the left arrow, and that's where metallic character increases. So in fact, if you go look at the periodic table, hydrogen is at the top left corner of the periodic table, and it's a non-metal. But below it is lithium, it's a metal. Then sodium, potassium, rubidium, cesium, and francium are each metals. The most metallic, so to speak, would be francium. All right, so let's define metals. Metals are elements that easily conduct electricity and heat. They tend to be hard materials and lustrous. You could also say they're malleable, or ductile. Malleability is the ability of an object to be hammered into shapes or compressed, squished into shapes. Ductility is the ability to pull something apart and create ultimately wires. So metals are hard, but they don't break easily when you add stress to them. You can, in a sense, hammer. Actually, here's a good example of malleability. People who win gold medals in the Olympics or other events, you'll see them bite the gold medal because gold is very famous for being so malleable or soft as a solid. You could actually bite into it and put teeth marks in gold if it was pure gold. Whereas something like steel, you can't. It's much harder. Don't bite into steel. But metals, whether it's steel or gold, they're all malleable to an extent. They can be shaped, molded after already being formed. You could take a hammer to them and the metal atoms will stay together and not break apart. Where if you take something that's a non-metal, those would rather break. Something like glass or ceramics, those just break, they shatter because they're brittle. Ductility is, again, pulling them from, like, let's say a chunk of copper. You can pull that and you can stretch it out into literally wires. It just gets thinner and thinner and thinner, and they wrap it around these like spools essentially, and eventually you get the copper wire or any other type of wire you need just by stretching them apart. Nonmetals, on the other hand, these are going to be elements. I'm going to change the color here. These are elements that poorly conduct heat and electricity, or they don't do it at all. They're insulators. They're not conductors. They tend to be brittle if solid, or gaseous. Most of the nonmetals are going to be gases at room temperature. But that doesn't mean you couldn't make them solid, but when they're solids, they're not going to be hard, malleable, ductile materials. All right, so semimetals, also called metalloids, these are elements that are just in between metals and nonmetals. What I would say is here, they sometimes have metallic properties and sometimes properties of nonmetals. There's not many metalloids. You could say there's boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine maybe, but that's a radioactive element that there's really not enough of to really know what its properties would be in this case. I would add carbon to the list. So it's not typically given as an example of a semimetal, but for carbon, you have many what we call allotropes of it, different forms of the same element. These allotropes you'll be aware of, you just haven't heard the word allotrope probably. You have the allotropes being diamond, graphite, coal, and I'm going to add graphene here. Diamond is a very hard material. It's the hardest known material, but it's not malleable, it's not ductile, it's very brittle. It does not conduct electricity very well, it's not going to conduct heat, it's an insulator, so it's very much a nonmetal. And the same would go for coal. It's a nonmetal. It's dull, black, doesn't look like a metal, doesn't conduct electricity or heat, it's definitely brittle. That's a nonmetal. However, graphite, although it doesn't necessarily scream metallic to you, if you look at it, it is a little lustrous. You know, graphite is in pencils. We don't use lead, we use graphite. They call it lead because they used to use lead. All right, if you look at the graphite, it definitely is shiny. It has a luster to it. But it doesn't necessarily look like a metal like all metals do. Here's the thing. It actually very well conducts electricity and heat. And it's soft. and therefore it'll be malleable and ductile to an extent. Not to the extent of something like copper would be, but it's definitely better at that than something like diamond. And so I would say that graphite it's certainly partially metallic because it can conduct electricity extremely well and heat. It has a luster to it. It's maybe more metallic than it is non-metallic. And then graphene is actually just graphite, but it's a two-dimensional, one atom thick layer of graphite. Graphite looks like chicken wire, but it's a bunch of chicken wires stacked on top of each other in 3 dimensions. Those layers are not very well held together, which is why graphite is used in our pencils. It rubs off very easily. And then graphene is just one of those layers. But graphene is the best conductor of electricity that we know of. And if that's the case, how could you not consider that to be a metal? So I'm going to put it here. You can actually get graphene by just taking a piece of Scotch tape and putting it onto a pencil, like sticking it to it and then pulling it off. And you'll see that some of the lead does come off, or graphite will come off. That should be about 1 atom thick and therefore technically be graphene. So overall, you have these different forms of carbon that have sometimes nonmetal, sometimes metallic. I would say carbon is a metalloid for that reason. When we discuss carbon, though, it's better to consider it to be a nonmetal as far as what's going on chemically. It behaves more similar to the other nonmetals like nitrogen and oxygen and fluorine and hydrogen in the way it bonds. It does not behave like the metals like lithium and sodium and potassium. So that's probably why it's not. But physically, it's, I would say, semi-metal. Chemically, it's way more often a non-metal. And actually, that reminds me, I should add in here something about their chemical properties, because that was all physical. Metals, I'm going to state here, these tend to lose electrons in reactions. In other words, they become cations. While nonmetals, they do the opposite. They tend to take electrons and therefore become anions. Or, so here's the next thing, is they share electrons instead of taking. Whereas metals don't often share electrons, they just give them up. And then semi-metals would, again, be in the middle. So I'm not going to add anything there. Carbon will most likely share electrons like nonmetals tend to do. Molecules are the smallest unit of a molecular compound. One key characteristic of a molecule is that they are capable of being isolated. Individually. While ionic compounds that we see below, you cannot isolate individual units of those. Molecular compounds are compounds in which atoms share electrons. To keep them together. While in ionic compounds, these are going to be compounds that have a complete transfer of electrons from one entity to another. And the atom that gives up the electron will be known as a cation. The atom that takes the electron will be an anion. So here we have 3 example compounds: water, ammonia, ethanol. Each of these are going to be molecular compounds where the atoms are sharing electrons. You can see water has the molecular formula of H2O, ammonia is NH3, and ethanol is C2H6O. The subscript numbers tell you the number of atoms of those elements. So water has 2 hydrogens and 1 oxygen. We leave out 1, it's unnecessary. Ammonia has 1 nitrogen and 3 hydrogens. Ethanol has 2 carbons, 6 hydrogens, and 1 oxygen. Now I'm going to point out here that the molecular formula doesn't tell you much other than what atoms are there. For example, there's another chemical called dimethyl ether, and it has a chemical formula of C2H6O as well. Structural formulas tell you how the atoms are bonded together. You can see water, ammonia, and ethanol there. The dimethyl ether would differ from ethanol in that it would look like this. So far it's the same, but you have a central oxygen, and then the second carbon is going to be to the right of it. So the carbons are no longer bonded to each other like in ethanol. The oxygen and the carbons have kind of switched places. They're completely different chemicals. They behave chemically different. They behave different in their physics, like melting point, boiling point, solubility, stuff like that. And it's just because of the structure of those 2 compounds. You can see for at least water, ammonia, and ethanol, the molecular model, ball and stick types, the molecular model, space filling types below. These are going to be the ones that are accurate to reality in a sense, like what the molecules that you could isolate, because these are molecules here, what they would look like if we could see them, or at least what we think they would look like. And again, by the way, just if we look at it, each of the elements in these 3 compounds, or 4 compounds, those elements are, chemically speaking, going to behave as nonmetals, or they're all nonmetals. You know, the carbon there, it's in a compound, so it's behaving as a nonmetal. And so these are all molecular compounds. The electrostatic potential map shows basically the density of electrons around the atoms in the molecules, where red represents high density, so a lot of electron density up here for water, and low electron density down at the bottom. We'll talk about that more in detail later on. Here we have an example of an ionic compound, sodium chloride. Sodium is a metal. It's shiny. It's actually soft. You could cut it with like a butter knife, but it conducts electricity very well. It just happens to be soft for a metal. Sodium reacts with water explosively often. It'll certainly catch fire if it doesn't explode. So sodium metal is very dangerous. You don't want to like mess around with it. Chlorine is a yellowish green gas, and it's extremely toxic. It's been used as like a chemical warfare kind of, gas to gas people. So it kills you, and these are both elements that will react with each other to make something we actually need for life, table salt, sodium chloride. All right, and you can see, I know this is just a, computer-generated image, but it's what the salt crystals of sodium chloride would look like. And it's just a repeated pattern of these ions. So you have the purple sodium cations, you have the green chlorines there, and they're just repeating. Now, it may not really look clear, but let's say this is a vertical line, and we can see there a corner of a crystal. All right, so like that would be the corner of a salt cube or something like that, where you have this sodium cation, then a chlorine, sodium, chlorine, and it just repeats until there's no more stuff left. There's nothing left. It repeats in the XY coordinate sphere, plane. It goes up and down, repeating that pattern in the Z coordinate. And so it's just what we call a lattice of these ions, and they're repeated. So if we were to take one sodium ion, right here, sodium plus, it wants to be surrounded by the oppositely charged chlorine ions, the Cl minus. As I mentioned, you cannot isolate ionic compounds, and the reason is, although this is neutral, the sodium atom is not very happy by only having that negative charge on one side of it. So it's more stable if it has a chlorine ion to its left as well, and a chlorine ion below it, and a chlorine ion above it, and then a chlorine ion in front of it. And I know I can't really show it, but there would also be one behind it. So in fact, there's going to be 6 chlorines surrounding each sodium, and the same would be true for the chlorides. There's going to be, I don't know how it changed to red, but whatever. There'd be a sodium to the left, a sodium below it, a sodium to the right, a sodium above it. There'd be a sodium behind it, and again, there would be a sodium ion in front of that chloride. And so that's the only way to like fully stabilize these ions, so they can't be isolated. They have to be in these lattices, and sure, there's going to be some edge to the lattice where the chlorides are not happy or the sodium ions are not happy. There's nothing on those other sides of them. But then things in the air, water, vapor, stuff like that can actually keep it together, and there's only so much you can do. At the edge of something, there has to be an endpoint where just those atoms are not fully stabilized, which is why ionic compounds actually are brittle. Like, it's easy to break them, in part because the atoms aren't stable anyways to begin with. All right, so here's a table comparing ionic compounds and molecular compounds. You see the particle types for ionic compounds will be the ions. For molecular compounds, you have molecules. The bonding types in ionic compounds, you have ionic, and that would be just opposite charges attracting each other. Whereas in molecular compounds, you have covalent, and that's where the sharing comes in. And we'll talk more about those later on, so don't worry about it too much here. And you see some examples. Sodium chloride or table salt is NaCl. Water's H2O. C3H8 is propane, like the gas we use in our grills. On this slide, we have a few ways of representing the composition of a chemical. We have chemical formulas, molecular formulas, and formula units. A chemical formula, simply put, just tells you the number of atoms of each element in a chemical entity. All right, so we have the number of atoms of each element in a chemical. So for example, water has the chemical formula H2O. Something like, let's use magnesium hydroxide has a chemical formula of MgOH2. All right. Water has 2 hydrogens and 1 oxygen atom. We'll leave out the ones because otherwise, if there wasn't at least one, it wouldn't be in the formula. Magnesium hydroxide, on the other hand, has 1 magnesium, and then it has 2 full groups of this OH unit. So in a sense, the 2 is applied or multiplied to the oxygen and to the hydrogen. I could rewrite the chemical formula simply as MgO2H2 if I wanted to, but there's a reason to keep it as this OH because it turns out the oxygen and the hydrogen are actually going to be bonded to each other, and there's going to be 2 groups of those OHs that are connecting to the magnesium. So it's more typical to leave it as is, and again, this 2 says there's 2 groups of OH. You could have another example, just thinking here, where you have like ammonium carbonate or something. That could be a compound where there's 2 ammoniums. The 2 here is going to tell you there's 2 nitrogens, and there's 2 times 4 hydrogens for 8. So in reality, it's N2H8CO3. There's 1 carbon and 3 oxygens there. So the parentheses matter. You got to make sure that you're understanding what it is saying. So this would be the true chemical formula simplified to NH4,2CO3 that tells you there's 2 NH4 groups. A molecular formula is essentially the same thing as a chemical formula, but it applies strictly to molecules. Again, you can isolate molecules individually. You cannot isolate ionic compounds, so it's the chemical formula of molecular compounds. Formula units are used for the ionic compounds, and the way to state this is that they are the simplest whole number ratio of ions in an ionic compound. So again, sodium chloride really has 6 sodiums for every 6 chlorines. Well, I could actually say it's 6 sodiums for every 1 surrounding each chlorine, or I could say there's 6 chlorines surrounding each sodium. So there's a 6-to-6 ratio, which is really just the same as a 1-to-1 ratio, so sodium chloride. You cannot isolate 6 sodiums and 6 chlorines anyways. You can't isolate 1 sodium and 1 chlorine grouped together, but it is the NaCl, a 1-to-1 ratio. That is the simplest whole number ratio of those ions in a sample of that ionic compound. So it is a formula, and it is 1 unit of those ions. Hence the name formula units. Going back to the molecular formula, like H2O is a molecular formula, MgOH2 is a formula unit technically. We can isolate, theoretically, 1 molecule of water because it is overall neutral, and so it's stabilized or stable in and of itself. All right, so now we have monomers, polymers, etc. here. Some chemicals will react with each other and link together in a fashion that creates massive, gigantic molecules that we call polymers. There are many natural existing polymers such as DNA, proteins, carbohydrates such as starch, glycogen, and cellulose are examples of naturally occurring polymers, and those are very ubiquitous in nature. but they each come down to having one single unit that is a molecule, essentially, that's going to combine with itself chemically like a chain. You know, you have multiple links in a chain and they combine together to make the whole thing. One link by itself is kind of useless. And for polymers, that single link would be the monomer. So it's a single unit of a molecule that can bind to itself or bond to itself repeatedly. I'm going to give you an example here, being glucose. Glucose is a single unit of a sugar. Our bodies use that to get energy from it. We convert the glucose. You know what? Its molecular formula is C6H12O6. I should write that. And we use that to convert it to carbon dioxide and water. But we also get energy by this process by producing ATP. You'll see that later. Now, monomers can sometimes link together twice or thrice or in small amounts to make these dimers. So this would be 2 combined monomers. And a trimer would be 3. There's tetramers with 4, etc., etc. So if they're small, you can call them dimers. If there's 2, 3, would be trimers, and so on. An example of a dimer, though, would be like maltose. Maltose is 2 times the glucose. They will literally chemically bond to each other to be one single molecule now, and that happens to be maltose, which is another type of a carbohydrate or sugar. Anything that has malted this or malted that, it has maltose in it. Oligomers will be usually 3 to 10 monomers long. They're not necessarily as common in nature, but they do exist. And then polymers, typically we can say 10 to infinity, in reality, monomeric units long. And again, I'm going to give you the example here of, let's say, cellulose, which is a polymer of glucose. Glycogen is another polymer of glucose, and starch is another polymer of glucose, but cellulose is the more abundant of those in nature. It's actually the most abundant carbohydrate that exists in nature. So here's the monomeric unit of glucose, the way it would look like in space. This is a structural formula here, and so you can see what's left out. This is for the organic chemists, or that corners are actually going to be represented by, or are going to represent carbon atoms here. So those ones I circled are actually carbons, and then all the other atoms are put in there. The beta and D glucose part you don't need to worry about for our purposes, but this is what a true molecule of glucose looks like. Then maltose, again, is a dimer. You can see they're linked together right there with that oxygen atom, and so it's a dimer of glucose. And then here I have starch, is, like I said, a polymer of glucose, where here's a glucose, there's one, and then it just repeats some number of times in that direction, and it would also repeat some number of times in that direction. Another example of a polymer would be like polyethylene terephthalate, or PETE, or PET plastic. So plastics, rubbers, silicones are each polymers, essentially. They're single, like once you get the polymer, that whole thing is one molecule. So if the number of repeated units was 8 million, then those 8 million units would just comprise technically one molecule, and its molecular weight or atomic mass would be, humongous compared to what the atomic mass of like ethylene glycol or terephthalic acid would be. This is an interesting reaction, though. You have ethylene glycol, which is in radiator fluid, or it is radiator fluid, and terephthalic acid, those will combine where technically the OH group here of the ethylene glycol will attack a carbon there and kick off water, essentially, in the presence of acid, of a different acid, I should say, because this is terephthalic acid, and create this unit. This unit here is the monomer. Now, that monomer is actually made up of two other subunits, the ethylene glycol and the terephthalic acid. But that monomer has this OH and that CO2H, just like the ethylene glycol had this OH and this CO2H right there. So it could react with a second molecule of itself by connecting through right there and creating something like what we see down there. And so technically this one is a dimer of PET, but again, the N here represents that it's going for some number of times that we're not counting to the left and to the right, you know, with a mixture of lots of ethylene glycol, lots of the terephthalic acid. It's just going to make one huge molecule. So I mentioned them a few times here. We have ions, ionic compounds, and those ionic compounds are compounds, chemicals that have two or more elements are compounds. But in ionic compounds, the atoms are transferring electrons. It results in the formation of ions. An ion is just an atom or a group of atoms that have fewer or more electrons than naturally occurring neutral atoms of those elements would have. And I'm going to put here in their ground state. All right, so for example, a sodium atom is going to have 11 protons. It'll have 11 electrons. It's balanced out, it's neutral at that point. But if the sodium atom, which has 11 protons by necessity, only has 10 electrons, well then it's going to be an ion. And that'll actually make it a sodium plus. If we have a fluorine, the fluorine is going to have 9 protons and 9 electrons, and it would be neutral by itself. But it doesn't really want to do that, actually. It's going to form an F minus with 9 protons and 10 electrons and also be an ion. So you can have more electrons than the neutral atom, or you could have fewer electrons than the neutral atom. Both of those are ions. Now, they're obviously going to be different if they have more or less, so we can classify them differently. Anions are ions that have more electrons than their neutral counterpart, and therefore they are negatively charged. All right. Just represent it as a minus sign. And so in the example to the right, the fluorine is actually an anion, what we call the fluoride. This is an atom of fluorine, and this is an atom or an ion of the fluoride. We'll talk about naming later, but technically they're different. Either way, we call it the F minus an anion. Cations are entities that have less electrons than they should, and so they're going to be positively charged. Or sorry, not less, they have fewer electrons than when neutral, and so are positively charged. I like to use this mnemonic. I don't know if it works for you, but I say cats are good because, you know, cations have a T, they're positive. Cats are positive animals, right? They make people happier, mostly. There's a T in the word cation. Maybe that helps you remember they're positively charged. Anions don't have a T. Onions are bad. Maybe you could use that. I don't know. I like onions, but anions are negatively charged. Cations are positively charged. Here's some examples of some compounds. Identify whether they are ionic or molecular. So first of all, I haven't mentioned that ionic compounds will exist between, typically, metals and nonmetals, while molecular compounds will be only nonmetals. And we're not going to worry about metalloids in these things. So when we look at CH4, you see carbon, you see hydrogen. Those are both nonmetals. So you would classify this as a molecular compound. Bromine is an element, but it's a nonmetal. Both of those atoms are nonmetals. Oops. So that would make this a molecular compound. Calcium chloride, CaCl2, has the metal calcium and the nonmetal chlorine. And let me do something here. Let's highlight metals in blue and nonmetals in red. So let's do that here. That might actually help. Now you could look at a periodic table as well and kind of figure that out. And because you have a metal and a nonmetal here, this is going to be ionic. Potassium is a metal. NO3 is a nonmetal. Both the nitrogens and the oxygens are nonmetals. So this is an ionic compound. CH4O is consisting of 3 nonmetals, so that's a molecular compound. And then LiF, lithium fluoride, has a metal lithium and the nonmetal fluorine, so that's an ionic compound. Predict the chemical formula for each combination of cation and anion below for an ionic compound. All compounds are neutral. This is a key fact here. So when you're making from ions chemical formulas, they have to combine in a way that results in no charge. So you're going to end up with sodium fluoride. You have a positive one and a negative one. Those balance out to make NaF. If we're doing the sodium and the sulfur has a -2 charge or 2 minus. We always put the magnitude, then the sign when we're talking about charges. And so since the sulfur has a 2 minus charge and the sodium has only a 1 plus, you need 2 sodiums to balance out the charge of the sulfur. So it's Na2S. If we're doing sodium and nitrogen, nitrogen has a 3 minus. So here again, we need multiple sodiums. In fact, we need 3 of them. And so it's Na3N, which is sodium nitride. Now, if we're using calcium, and we're looking at the fluoride there, you have a 2 plus and a 1 minus. So you're actually going to need 2 fluorides here. So it's CaF2. Calcium to sulfur, you have a 2 plus and a 2 minus, so they balance right there. CaS, calcium sulfide. Calcium in the nitride there, the N3 minus. You have a calcium, well, there's a 2 and a 3. You can't have 1 calcium. You can't have 2 calciums, or even 1.5, because you can't have half of an atom. So what you do is what's called the crisscross method. You could do this for any of these, but here is where it really shows you the value of it. If we take those charges and we just change them to Ca2 and N3, and then take those numbers and put them as the subscripts on the opposite atom, we'd get Ca3N2. Because, well, 3 times a 2 plus is a 6 plus, and 2 times a 3 minus is a 6 minus, and so those balance out, and we get that. And the crisscross method works for all of them. If we did the calcium and the sulfur, you could maybe rearrange it to be, get rid of the charge. It doesn't necessarily matter. If you use the crisscross method for this, you get Ca2S2, but we have a metal calcium and a non-metal sulfur. It should be an ionic compound, and its formula unit should be the simplest whole number ratio, and that for a 2-to-2 ratio is a 1-to-1, so again, it's just CaS. You have to remember to reduce it if possible. Whereas in calcium nitride, you can't reduce 2 and 3 any further. Or you could just look at it mathematically and say, what's the least common multiple of 2 and 3? It's 6. How many times you have to go from 2 to 6? It's 3. So Ca3, how many times you have to go from 2 to 6? Or sorry, not 2 to 6, 3 to 6. It's 2 times, so it's N2, Ca3N2. And then with aluminum, you have the 3 plus, so it'll be aluminum fluoride, AlF3. Aluminum and sulfur will do the same thing, Al2S3. Notice this was 3,2, this is 2,3. It's just switched because the fluorine now has the 3 and the sulfur has the 2. And then somehow, I should write that in there. And then finally, aluminum and nitrogen will be at a 1-to-1, so it's just AlN. If you did the crisscross method, you get Al3N3, but reduce those to the simplest whole number ratio of those. All right, section 8, we're going to name simple compounds. The word nomenclature just means naming, so chemical nomenclature is just how to name molecules, or compounds, I should say. When we name monatomic ions, these are ions that have one atom in them. If they're cations, they have the same name as the element. If they're anions, I'm going to do this in a different color, they're going to take the suffix of the name of the element and replace it with "ide." as a suffix. So for example, if we have the sodium ion here, this is just sodium, the sodium cation. If we have an F minus, it goes, well, by the way, this was sodium, and F minus comes from fluorine. And so you take off the ene and replace it with ide, so it becomes the fluoride anion. Or you could just say it's the sodium ion or the fluoride ion. Polyatomic ions are ions that have multiple atoms bonded together covalently. And we'll talk about covalent bonds later. But they're bonded by sharing electrons, and they form this group. But that group can be itself charged. So examples of those, I already brought up some of these before. An NH4 plus is an ammonium ion. There's Hg2 plus, which has 2 mercury ions. Technically, this is a mercury 1 ion is how we would name that. We'll see that later in the rules. Those are some polyatomic cations. There's many more polyatomic anions, though. Examples being just a few here. SO4 2 minus is known as the sulfate ion. Maybe NO3 minus is the nitrate ion. They don't all end in 8, so let me give you an example. One that doesn't. Let's do ClO minus. This is the hypochlorite ion. So they don't end in "ide." That's the difference. The monatomic ones always end in "ide." Polyatomic ions have their own special names or ways of naming them, but you'll be given tables with those to look at to help you figure out what the name of a chemical is. So naming simple ionic compound rules here. 1, never use prefixes with ionic compounds. Prefixes meaning like numbers, like di, tri, tetra, etc., representing the numbers of things. You don't use those for ionic compounds. Rule 2, common cations and anions, including polyatomic ions, are listed on the next couple of pages or slides. If the cation has only one possible oxidation state or charge, simply name the cation and the anion. So for example, this is just named sodium fluoride. If we have NH4 SO4, NH42 SO4, its name is simply ammonium sulfate. Now you'll notice there is no metal in ammonium sulfate, but it is an ionic compound because the ammonium is positively charged and the sulfate is negatively charged. In the chemical formulas, we always list it as cation and then anion. All right, and the same goes with the name. So any atom that has like one possible charge will fit here easily. Those are groups 1 through 8 of the periodic table in Roman numerals. It might actually be listed as 1A through 8A, like that. Or it might be listed in the groups 1 and 2 and then 13 through 18. It just depends on the periodic table. But suffice it to say, if I'm drawing a periodic table, you have these groups like that and then the ones below it. This works for the parts on those edges, not the middle or down there. All right, so naming these ionic compounds, again, let's just make sure they're ionic. You have a metal calcium, you have a metal aluminum, you have a metal barium, you have non-metal chlorine. You actually have a metal chromium there, but this actually ends up being a group. Because it's a group, it's a polyatomic ion, and therefore it's not a metal. We have this group here and this group there. Both of those are polyatomic, and because they're polyatomic, that is a nonmetal, and also that's a nonmetal, but it's kind of one of those things where you sometimes just need to memorize some of these, and you'll see the list later of polyatomic ions. But if you see NH4, if you see NO3, those are polyatomic almost all the time, especially when together. So we have calcium chloride. You just name the species there. You'd find the NH4 to be ammonium, the NO3 to be nitrate, so it's ammonium nitrate. Calcium chloride, by the way, is used to salt roads for winter times in cold places where it snows and freezes over. Often ammonium nitrate is in fertilizer. The next one is aluminum chloride. And the last one is barium chromate. All right, naming ionic compounds with transition metal cations. Those are the ones in the middle portion of the periodic table. So we're not going to worry about there or here. Strictly this region. Those are the transition metals. So if the cation is in that region, those atoms can have multiple charges. Like iron can have a 2+ charge or a 3+ charge. Manganese can have a 2+, a 3+, a 7+, whatever. It has a lot of different options. And so the naming rules have to be different for those than for the ones where there's only one option. An older, outdated nomenclature system exists for cations of transition metals such as iron, which is Fe. Most transition metals can have variable charges, as I mentioned. Thus, they must be named differently, such as OUS as the suffix and IC as a suffix. So iron comes from its Latin name ferrum, and it can have different charges to it. And when you get that, you can have two different compounds, FeCl2, for example. It can combine with chlorine to make that, or it could combine with chlorine to make FeCl3. Chlorines always have a -1 charge, or a -1 charge, I should say. And so what that would tell you is that this iron here is an Fe2+. The iron there is an Fe3+. They're different. They must have different names. The compounds, therefore, will have to have different names. So we have ferrous chloride and ferric chloride. The problem is that with this naming system is that the OUS, the IC, do indicate like the lower oxidation states or charges to the higher, but it's not always a 2 and a 3. It could be a 1 and a 2, a 1 and a 3. And then some other elements like manganese have more than 2 oxidation states or charges, and this naming system became obsolete as a result of those types of situations. So we developed a new one where you use Roman numerals. So this system, however, can be unclear when more than 2 charges are possible. Thus, the Roman numeral system or stock system for the naming is currently the proper nomenclature method. In the stock system, you use Roman numerals with no space between the cation and the numeral in parentheses to identify metal charges with transition metals. Therefore, a copper 1+ ion would be called copper 1, and a copper 2+ ion would be called copper 2. For examples here, we have FeCl3 again. This was ferric chloride. It's now going to be just iron 3 in the parentheses there, Roman numerals, iron 3 chloride. And that's how you say it too. The next one, you have this NO2, which is a nitrite ion, and there's 2 of them. The nitrite is always a 1- charge, and therefore, because you have 2 of those, the iron must be a 2+. So this is iron 2 nitrite. All right, so we have here a table with monatomic ions of the quote-unquote main group or representative elements. And you see group 1A, we have all of them with a 1+ charge. Group 2A, they all have a 2+. 3A, except for tellurium there, they have, or thallium, they all have a 3+ charge. Group 4, we typically ignore this, so just don't look at that group. And then group 5A, really we'd see the same thing. We're going to start ignoring these because they become metals down there. You could just, whatever. And then group 6A, 2 minuses and 1 minuses. For those, you see hydrogen is actually listed there as H-, but hydrogen also is sometimes listed as an H+. We'll talk about hydrogen and its strangeness later with the charges and stuff, but what you see here are what these atoms as monatomic ions will have. I'm going to put in the H plus because that's typical. The reality is H plus doesn't exist, but it's almost as if it does exist when we talk about chemical reactions. All right, here we have some transition metals and their multiple ions. You see in this transition metal group, certainly not all of them have multiple charges, but most of them do. So we use the stock system for those. Silver only has the 1+ charge. So if we had something like silver and chlorine, it would just be AgCl, and you would name it silver chloride. Zinc only has a 2+, so this is ZnCl2, and you just call that zinc chloride. You don't need to include the Roman numerals for those because they only do have one charge. Silver chloride and zinc chloride. Nickel, though, it would be nickel 2 chloride and nickel 3 chloride. You'd have to name it because they have multiples. Here's the list of the common polyatomic ions. You see the only two they have here that are cations are the mercury 1 and ammonium ions. The rest are going to be anions, negatively charged. Ones maybe to focus on, you'd have the acetate, the carbonate, the nitrate, phosphate, and sulfate ions. Maybe hydrogen carbonate because that's in baking soda. Those are certainly things to, oh yeah, and I missed one, the hydroxide. That would be another very important one. All right, now here we have really the same thing. It's just organized in a much clearer way based on elements. So you see polyatomic ions with hydrogen, you only have the hydroxide. With nitrogen, you have the ammonium, which is positive, the nitrate, the nitrite. With chlorine, notice you have 4, 3, 2, and 1 oxygen, and it goes from perchlorate to chlorate to chlorite and to hypochlorite. Now, the reasoning for those names would be that this actually comes from hyperchlorate, hyper meaning above. It's above the chlorate. It has one extra oxygen there. So the chlorine actually would have a higher oxidation state than in the ClO3. And then you go to chlorite and then hypochlorite. Hypo means below, so it's below chlorite. But for whatever reason, they took out the HY of per, anything with per, so it's just perchlorate, not hyper. And the same thing would follow for other species. If you had SO4, you see it's sulfate. SO3 is sulfite. If there was an SO2 ion, it would be hyposulfite, but that doesn't exist. Carbonate is CO3 2-. CO2 2- is the carbonite ion that Han Solo is frozen in, except CO2 is not going to be a -2 charge. So carbonite doesn't actually exist. Here's some more. These are compounds that have polyatomic ions, and their medical uses: aluminum phosphate, aluminum sulfate, and so on and so forth. All right, naming simple molecular compounds. We have binary compounds. These are compounds with just 2 atoms or 2 different elements. And they're molecular. All right, so naming these binary molecular compounds. First, name the first element present, followed by the second element. Let me give you an example here. If we had, let's say, NO2. This is nitrogen, right? First, name the first element present, followed by the second element. Usually the first element is located furthest left and or furthest down on the periodic table. the suffix "ide" should be used with the second element. So this is oxygen, right? Then it's not nitrogen oxygen. It's nitrogen, and we change the "igen" part to "ide." So nitrogen oxide. Use prefixes now to indicate the number of atoms or groups of atoms in these. So use mono for 1, di, tri, tetra, penta, hexa, hepta, octa, nona for 9, deca for 10, etc., etc. It goes on forever to indicate the number of atoms of each element in the compound. Since this actually, NO2 has 2 oxygens, you're going to name this nitrogen dioxide. Now, mono is emitted from the first named element in the compound. So we could say mononitrogen dioxide, but we just eliminate that out, and it's nitrogen dioxide. If we had something like NO, this we have 1 of each, it would be nitrogen monoxide. It's not monooxide. For whatever reason, if it's oxygen, they just say, just delete that out. It's nitrogen monoxide. Just like CO is carbon monoxide. And CO2 is carbon dioxide. All right, those, or when the first element is, there's only 1 atom of those. Let me give you one more. HCl is hydrogen monochloride. It's acceptable, though, to say just hydrogen chloride. For whatever reason, no one cares for that particular one. That's why I wanted to bring that up. If you have something like, let's say, N2O4, this would be dinitrogen tetroxide. Tetra means 4 in Greek, and we're using Greek prefixes here. So it becomes tetroxide. Again, you get rid of the A. It's not tetraoxide, although that would be better. So that's the 4, this is the 2. These are the elements, nitrogen and oxygen. Always the first one keeps its suffix and the last one changes to the "ide." All right, we have more examples here. This would be iodine monochloride. We already did that. It's nitrogen dioxide. Carbon tetrachloride. In this case, because it's not oxide, you do keep the A, so it's tetrachloride. And then we have tetraphosphorus triselenide from selenium. Here's some more binary molecular compounds. Again, they have 2 elements only. Carbon dioxide, carbon disulfide, dinitrogen monoxide. And you can see what they're used for. Nitrogen monoxide, sulfur dioxide, sulfur hexafluoride, sulfur trioxide. All right, flowchart for naming these chemical compounds. So far we have ionic compounds and then the binary molecular compounds. Here you can see what to do if they're if they're ionic compounds. You have a metal and a non-metal. For the metal, you just name it, like sodium or ammonium happens to be one of the 2 polyatomic cations. If it forms only 1 positive ion, you use the name of the element or ammonium, or just the name of the, if it's polyatomic, whatever, it's already been defined as its name. If it forms more than one positive ion, you use the stock system with the number as a Roman numeral, the number representing the charge. For the nonmetal, if it's a monatomic ion, use the first syllable of the element name followed by "ide." For the polyatomic ion, use the name of the polyatomic ion. If it's binary, first will be a nonmetal, second will be a nonmetal. Use a prefix to match the subscript before the element name. Like, again, it was dinitrogen and tetroxide. Use the prefix to match the subscript before the element name and end with "ide." All right, naming simple acids. First of all, you need to know what an acid is in order to recognize when you're naming an acid versus maybe a binary molecular compound or just other molecular compounds. Acids are chemicals, simply put for now, that when dissolved in water produce H plus ions. Or in reality, those are not H plus, but H3O plus ions. They tend to taste sour. Anything that's sour is going to have a bit of acid in it. So they produce these H plus ions, so to speak. Technically, they're going to give up a hydrogen to water. So an example of an acid is HCl. HCl is actually a strong acid. When HCl and water come together, they make H3O plus and a Cl minus. But we could also, the extra hydrogen on that water in the H3O plus can kind of just behave as if it's an H plus ion by itself. So we could simplify this process to being an H plus and a Cl minus. This thing is going to want to do something as an acidic hydrogen atom, also known as just a proton. If it's a hydrogen 1 atom, it has 1 proton, 1 electron, and 0 neutrons. So if it loses its electron by becoming H plus, then it's really just a proton. That should be a red flag for you that it won't exist by itself, because protons are not atoms. So it's not actually an H plus. It's just the water is willing to give up one of its hydrogens when it has an H3O plus formula, and so it can use that hydrogen to do stuff. So it's treated like it's an H plus. Okay, so HCl we saw earlier was named hydrogen monochloride. That's actually only when it's in the gas phase, do we call it that? When it's not in the gas phase, it's probably in the liquid phase, dissolved in water, and then it behaves as an acid, as we see in the reaction there. And when that's the case, it's called hydrochloric acid, which is the acid in your stomach. That's stomach acid. Now, there's no oxygens in hydrochloric acid, so it's not an oxo acid. Oxo acids are acids that contain oxygen in the anion. In fact, the first definition of acids all were chemicals that had oxygens in them. They were oxo acids. The name oxygen itself means to generate acid. And so, like, Antoine Lavoisier is the guy who discovered that. A lot of these oxygen-containing compounds were acids, so that's why he called oxygen oxygen. Examples of oxo acids would be sulfuric acid, nitric acid. Those are the two most common. Maybe phosphoric acid would be next, H3PO4. Those are oxo acids. And we saw a bunch earlier. We had ClO4 minus, but if you have the H there, it'd be HClO4. HClO3, HClO2, HClO, those are all oxo acids. You have HNO3, HNO2, H2SO4, H2SO3, H2CO3, those are all oxo acids. For acids that do not contain oxygen, follow these rules. If the acid ends with the suffix "ide," add the prefix hydro to the front of the name. Change the suffix from "ide" to "ic," and then add the word acid at the end of the name. So again, this was hydrochloride. It comes from the chloride, so it becomes hydrochloric acid. If we have something like H2S, this would be hydrosulfuric acid. Just to remind you, H2SO4 is actually just sulfuric acid. So we have sulfuric acid and hydrosulfuric acid. Name the following simple acids. Again, we've already done HCl. I'm not doing that again. Water is H2O, but if we're treating water as an acid, this would be hydroxyic acid or hydroxic acid. If we're treating it as a simple binary compound, well, then it would actually be dihydrogen monoxide. But simply put, water. HF is hydrofluoric acid. I already did H2S. HBr would be hydrobromic acid. And HI is hydroiodic acid. For simple oxo acids, use the names of the anions that would form resulting from the removal of the acidic hydrogen as a starting point for naming the acid. In other words, find the polyatomic ions name. Right? If we have HClO4, just take off the hydrogen. You get H plus and then a ClO4 and a 1 minus, right, to make it neutral. And so now name that. If the anion's name ends in 8, change the suffix to "ic." All right, so this is a perchlorate ion. All right, so we're going to call it perchloric. Add the word acid to the end, so it's just perchloric acid. Next, if we have HClO3, that goes to H plus and ClO3 1 minus, and that has the name of chlorate. So its name is just chloric acid. All right, if the anion's name ends in ite, ite, change the suffix to "us and then add the word acid at the end. So for like HClO2, this becomes the ClO2 minus ion, which is the chlorite ion. And so the acid name is chlorous acid. And then HClO goes to H plus and ClO minus. This has the name hypochlorite ion. And so the name of the acid is hypochlorous acid. All right, so we have the carbonate ion would be carbonic acid. NO2 minus is nitrite, so it would be nitrous acid. NO3 minus has the nitrate ion, so that's nitric acid. PO4 3 minus has the phosphoric acid. SO3 2 minus is sulfurous acid. SO4 2 minus is sulfuric acid. And then the HClO, HClO2, HClO3, HClO4 in their names. So if you look at those, we have those. squeezing in here HCl, we have hydrochloric acid. So with chlorine and hydrogens being the thing, notice the acids all have hydrogens on the left. Water is one of a few that's really not an acid, but the hydrogen's on the left there. But that's a good indicator if it's the first element listed that it is an acidic compound. And you can see go from perchloric to chloric to chlorous to hypochlorous, and then finally hydrochloric acid. So name the following oxo acids. All these were on the previous page, I believe. We have nitric acid and nitrous acid. I already did all of those. I see that there's a typo here, so I apologize for that. It should be H3PO4 to be phosphoric acid, and then carbonic acid, and then I have the H2CO2 would be carbonous acid because it comes from the carbonite ion, although it doesn't actually exist. That, again, was just a joke. Carbonous acid does not exist. All right, the last bit here are hydrates. Hydrates are ionic compounds that have molecules of water attached to the crystal structure. They're actually adhered to it inside and outside of the structure, so they actually become a part of the compound, so to speak, although they're not chemically bonded to it. Anhydrous compounds would be those hydrates who have had the water removed. Or driven off by heat. Well, it could be heat or it could be by low pressure. By the way, if you put something in a vacuum, it would drive off the water as well. So an example of a hydrate would be copper sulfate, pentahydrate. We put this dot in the middle there to represent that what comes after it is not chemically bonded. But each formula unit of copper sulfate is going to have 5 molecules of water surrounding it in the solid crystal of copper sulfate. For anhydrous compounds, we drive that off and we just get copper sulfate, CuSO4. Naming hydrates, add the word hydrate to the end of the name of the anhydrous compound. So if you ignore these, we have magnesium sulfate, and then we have copper, make that an O, not a U, copper 2 sulfate is technically its name. Then we add the word hydrate to the end of the name. And I probably should put another rule in here that you use prefixes for the number of H2O units or molecules that are attached. So MgSO4 7H2O is really magnesium sulfate heptahydrate. That is its full name. And then CuSO4 5H2O would be copper sulfate pentahydrate. That's the full name. This whole thing is the name of MgSO4 7H2O, and that's CuSO4 5H2O. If you heat these up and you get rid of the water, it's just magnesium sulfate and copper 2 sulfate. And those would be anhydrous. All right, that is the end for our chapter 2.